All right, now we're going to begin an analytical approach for describing a function. And what that means is that we're going to use calculus to precisely describe the graph of f of x. All right, to begin with, today's lesson is focusing on where a function is either increasing or decreasing using analytical methods. There's a corollary to the mean value theorem that states that we can find where the function is increasing, and that occurs when the first derivative is positive. So if the first derivative is positive, f of x should be increasing, and if f prime of x is less than 0 or negative, then the function f of x will be decreasing. Well, here's the main idea for that. So I'm going to draw a curve. All right, so if f of x is increasing, so that essentially it's rising to the right? And then if I put a little tangent segment on there, right, what would be the slope of the tangent? Well, I have no idea what that slope is, but I for sure can tell that it's a positive slope. And so I know that the first derivative, f prime, will be greater than 0. And that occurs on a section of the graph where f is increasing. Similarly, if f is decreasing, so that means it's falling to the right, and then I would have a section of the curve that has this appearance. And if I draw a tangent segment on there, my tangent segment should have a negative slope, which means that f prime would be negative. All right, so how can I distinguish using analysis where these regions are occurring? Well, the best way to do it is to study where it's not positive or negative, and that would be at a place where there's a horizontal tangent. So typically at the peak or valley of a curve. So right here, I have a horizontal tangent, and I have f prime equals 0. So we can use this location to help differentiate the sides that are increasing and decreasing. That is the main idea. So, and then similarly, another place that will differentiate positive and negative would be if I had a curve that looks something like this. We all recognize that as a cusp, right? Well, obviously, if I draw a tangent slope on the left side of the curve, well, that looks like it's a positive, so f prime is positive there. And tangent slopes over here on the right side of the curve are negative, so f prime is less than 0. So I do see that change again, f prime greater than 0, f prime is less than 0. So there is a change from increasing to decreasing using the derivative. But here at the peak, the tangent slope is undefined. So I would have f prime is undefined. So undefined values of the first derivative, undefined. So undefined values of the first derivative are also places that distinguish a change in sign and a change from increasing and decreasing. So I'm going to use that as my strategy. I'm going to type that up. So a strategy that I'm going to use is that I'm going to look for where the first derivative, so f prime, is equal to 0, or where f prime is undefined. And then I can use those to distinguish around it where f prime must be positive and negative. Okay, so let's take a look at this graph of f of x. So it's a cubic graph. We need to do a first derivative, so f prime of x. All right, so take the derivative of each term, power rule, so that would be 6x squared. The next term is minus 18x. And then the next term is plus 12. All right, so the strategy we're going to look for is where is this derivative equal to 0 or undefined? Now, this function, the first derivative, is defined for all reals, so there are no undefined values. However, it might have some zeros, so I'm going to set this equal to 0 and then solve that quadratic equation. I'm going to begin with by dividing everything. There's a common factor of 6, so I'm going to divide both sides by 6 and simplify this polynomial down. So that would give me, dividing by 6, that would be x squared, and then dividing 18 by 6, that would be 3 minus 3x. Divide 12 by 6 is 2, and then divide 0 by 6 is 0. So I simplify the polynomial down for solving purposes, and then I can easily factor this. This is x minus 2 times the quantity x minus 1. And there are 2 zeros for this function. So so the 2 roots of this are x equals 1 and x equals 2. All right, so remember that, so that's where my horizontal tangent is. So now I need to test around it to find out where my first derivative is positive, where the curve is increasing or decreasing by evaluating the first derivative around it. Now, the way that you can do this, there's 2 ways to tackle this, and one is to use a table. So essentially what I'm going to do is I'm going to divide this up into my domain for the first derivative into regions and test around it. So what I mean by that is my domain intervals for the first derivative. Okay, so I have all the values to the left of 1. Well, that would be negative infinity to 1. Okay. And then I have all the values between 1 and 2 to find out what's going on with the function in there. So that would be between 1 and 2. And then finally, I have my last interval from to the right of 2. So from 2 to infinity. So essentially what I'm doing is I'm studying on a number line what's happening with my first derivative around these 2 numbers. And so I have 3 different regions to figure out where it's increasing and decreasing. Now I know at 1 and 0 that my f prime is exactly horizontal. So I have, it's equal to 0 there. All right, so I have horizontal tangents at that, but what's the value of my first derivative around those horizontal tangents? So I'm going to pick an x value in each interval. I just choose something. So what would be a number in this region? I could choose, how about something, always keep it simple. So to the left of 1, I would probably choose 0. And then in between 1 and 2, I would probably choose x equals 1.5. And then to the right of 2, how about if we choose x equals 3? Integers are always best. Okay, now I need to know what's happening with my first derivative at each of those points, right? I want to know if my first derivative is positive or if it's negative. I know it's not equal to 0 because I found the only 2 zeros. All right, so I'm going to plug in 0 into my first derivative. So f prime of 0. Okay, so I plug it in. Now, I can use any one of these forms, the factored form, the reduced form, or the original form. It doesn't really matter. They will all produce the same result in terms of sign, because that's what we're looking for here. I'm trying to figure out if it's positive or negative. That's all I care about. So if I plug it into the original, that would be 6 times 0 squared minus 18 times 0 plus 12. Well, that would all simplify to just 12, and 12 is a positive number. So this would be equal to 12. I'll put the actual value, but what matters is that it is positive. So everything to the left of 1 would have positive tangents. So f prime is positive on the left side of 1. Okay, all right, what does that tell me? That means that I actually can draw a conclusion. So f is increasing. F of x is increasing on the interval on the left side of 1. So on the interval from negative infinity to 1. Okay, so I have that much. And so now let me test a number inside here. So 1.5. Now, I can use either one of these forms. If I plug in one, I'm going to use the factored form. Now I'll show you why I like to use the factored form. So I'm evaluating f prime at 1.5. All right, if I use the factored form, really all I have to do is I'm plugging in 1.5 right here, 1.5 minus 2 and 1.5 minus 1. Okay, if I do the first one, I get something that is negative. 1.5 minus 2 is going to be a negative number. If I plug it into the second factor, I get 1.5 minus 1, and that's a positive. All right, and then all I have to think is what's the product of a negative and a positive? It's going to be negative. So this region, we're getting negative tangents. My first derivative is less than 0, so my function is going to be decreasing. So I can make a conclusion right here. So f of x is decreasing on the interval from 1 to 2. All right, one final region. Let me go ahead and put this on my number line. So in between 1 and 2, my first derivative is negative. And so f is decreasing, right? So if I do a second part up here, f is increasing here on the first interval. F is decreasing in the second interval. And then in this one, we're going to find out, take a guess, x equals 3. Okay, so f prime of 3 is equal to, all right, well, 3 goes in. 3 minus 2, oh, that's a positive. 3 minus 1, oh, that's also positive. And so the product of two positives is something positive. Okay, so I have something positive here. What does that tell you about f? Since the first derivative is positive, that means f is increasing. Oops. All right, positive first derivative, f is increasing. All right, so I can add that to my increasing sentence. So union, and that would be from 2 to infinity. Right now, so this is essentially the answer. On an AP test, on a free response question, you would have to give a justification for this. This work here would not count as a justification. So on a free response question, you would have to complete this sentence with a reason. And so we would say something like, because, and the reason we got it was because the first derivative is greater than 0. All right, same thing with this one. This f of x is decreasing on this interval because f prime is less than 0. And that completes this example. Now, just as far as your work product is concerned, typically this part right here is what students use. They usually do this testing of intervals using a number line. But if you prefer, you could certainly do a table. So I have presented both to you. So you choose when you're working problems, do you like to do it as a table or do you like to do it as a number line? Both are ways to organize your work and your ideas. But the answer is in the sentence here. You have to answer the question, and we have two results in these two statements. Okay.